Eugene is from the same lab like me. We are working together in EPFL for 3 years or 4 years. 4 years. And but I'm working on the chemistry parts, and Eugene is on the physical chemistry side. And as I know, Eugene works a lot on the liquid interface and the assembling of gold nanoparticles on the surface for liquid optics and electrocatalysis, as you can find from the title. And Eugene has published about 20 papers on ECS Nano, chemical review and chemical science, the top journals. So today it's a great honor for us to invite Eugene to give us a presentation on the topic of assembly of gold nanoparticles and liquid interface from liquid optics to electrocatalysis. And let's welcome Eugene.
Thanks, Liang. My pleasure to be here. Actually, we were with Liang office mates.
Yeah.
So we were sitting just next to each other in Lausanne. Okay. As Liang said, today my presentation will be devoted to present you my work that lasted for 5 years on assemblies of gold nanoparticles, and I will try to talk about application and properties of these assemblies, and maybe some of you will find some part of this presentation interesting and applicable to your own research. So this is a small outline of this presentation. I think I will not go through every point, but I will try to give you a sense of with what I was working and what results I achieved. And if you want some conclusions and maybe some additional information, there is a book published in Spring Apprentice series, so please download and enjoy reading. There are 300 pages, you will definitely enjoy reading. Briefly about LEPA and the EPFL. So after some time we moved from Lausanne to Sion. Sion is here. It's middle of Canton Valais. Actually, some of you know where it is. And we have two sites. One is Martigny, another is in Sion. In Martigny we have such a nice building with battery, redox flow battery installed, because main focus of Professor Giroux research nowadays is redox flow batteries, where we convert electricity from solar panels to fuel, like to electricity back or to hydrogen. And in Sion, we have a normal lab, like you have here in Fudan University. So this is how it looks like, and we are about like 20 people, so master students, PhD students, and postdocs. LEPA, it's a laboratory of physical and analytical electrochemistry, so it means that we are kind of like split between analytical and physical electrochemistry. And these four, it was before, these three, what we are doing right now. And in physical part, we also dropped energy conversion and supercritical reduction and focus more on transfer soft interfaces, electron transfer soft interfaces, and redox flow batteries. And there are main areas of our research, so we still ongoing. We're still doing some research with the mass detection of some bacteria and cells. We also have a small group that is working on SCCM, so scanning electrochemical microscopy, doing more or less the same, trying to distinguish cancer cell, living cell, dead cell, and so on. And as I said, for let's say physical electrochemistry, we are more focused on solid boosters for redox flow batteries. Yeah, great. This is just a small scheme, a small roadmap to describe where we started and where we went. So we started with TTF-assisted assemblies of gold nanoparticles at liquid interfaces. Then we investigated optical properties of such assemblies, including making some electrovariable optics, let's say optical elements like shutters. We did big, large-scale mirrors and filters. Also, a big part of the research was devoted to electrocatalysis and electrochemical properties of such nanoparticles at liquid-liquid interfaces. And I think today maybe these two parts, especially for people from Bauhaus group, will be interesting. This is assembly at low interfacial tension and microcapsules formation at liquid-liquid interface. As Liang said, at some point last year we published a chemical review, and I'm really happy that we compacted all this 5-year research in one big review with some perspectives. And yeah, as I said, today I will talk about these, then assemblies at low interfacial tension, then some methods how to prepare films at liquid-liquid interface without shaking at very flat interface. Then I think I will skip this part because it's too theoretical. I will talk about interfacial electrocatalysis for oxygen reduction, and I will show how nanoparticles can actually work at liquid-liquid interface. And finally, yeah, I think for perspectives I will talk more about self-termination welding and how we can use this as a very easy process to make porous gold electrodes. Why liquid-liquid interfaces? Very simple answer, because these interfaces allows us and give us defect-free platform with very homogeneous, energetically homogeneous interface. So normal interfaces like liquid-solid, solid air, and so on, they are inhomogeneous or heterogeneous. And here we are playing with homogeneous, and this simplifies many things. These interfaces were shown to be used to assemble various types of nanoparticles, nanoparticles like molecules, for example, molecules assemblies, nanoparticles, even micro objects, like really you can cover a drop of oil in water with micro objects, and this is well-known pickering emulsion that you eat every day as a yogurt, as some products like cheese, for example. And also these interfaces, they have self-healing property, and they have very high transparency that is good for optical applications. So today's message for you, I think it's from me to you, that liquid-liquid interfaces is almost the perfect system to assemble nanoparticles and study these assemblies. Couple of words about plasmonics for whom doesn't know about that. So if we have a metallic particle full of electrons, if we apply some external electric field, like light, for example, then we shift electronic cloud. We have positively charged core. We have a dipole. This dipole starts to oscillate, and oscillation of this dipole we see as a peak of abnormal absorption here, on somewhere in the visible range. And this is pretty clear, visible when you synthesize different sizes of nanoparticles, and different sizes of nanoparticles gives you different colors. We used pretty common synthesis, so nothing special. We took source of gold. We use some reducing agent, heat it up, and we finish with such nice red. So we started with yellow, but we finished with a red solution of nanoparticles. Further, why we played with that? Actually, before I came to Switzerland and before I joined the group of Professor Giraud, there were several works published on the topic of self-assembly of nanoparticles at liquid-liquid interface, and the idea was, can we use external fields like electric or magnetic to drive nanoparticles to the interface or from the interface of two liquids, and thus form filters or mirrors and so on. And can we understand somehow the assembly process? Because so I joined it in 2012. So for 5 years, in 2013 I started more closely working on that project. For 5 years there was no progress. The theory was there, the idea was there, and there were no progress. So we really need to understand the self-assembly process at liquid-liquid interface. And the main problem for self-assembly of nanoparticles and any object, it's a relatively high barrier that nanoparticles have to overcome to be absorbed. The second problem was that the films that were reported in the literature at that time, they were brittle, they were form cracks easily, so you shake and it breaks apart. And if you still want to do some really good films, then you need really very expensive functionalization of nanoparticles. And in principle, Bohr showed that this functionalization might work, and this is a very good example of magnetically driven mirror. For me, I classify all the self-assembly methods in two big groups. The first one is zero surface tension, when you somehow form the third phase, and where the properties of the liquids changes gradually, not like in stepwise at liquid-liquid interface. So, for example, you add some ethanol, you mix, and you assemble nanoparticles. Another one is reducing charge of nanoparticles. This can be done by different words, let's say promoters, salts, additions, and so on and so on, but the idea is still similar. You increase the concentration of the salt, you decrease the repulsive forces between nanoparticles, you assemble them. Again, when I came, there were several works on this molecule, TTF, TTF, that can be solved only in organic solvents, but if you oxidize it, you form cation radical, and this cation radical can already be solved in both phases, organic and water. The idea was pretty simple. Okay, let's a lot of sulfur, so let's try to use these to assemble gold nanoparticles. Also, we should form some charged species, so it should promote the assembly. Okay, fair enough. And maybe we need to add some shaking to increase the interaction. As a result, we took 1 millimolar TTF solution in dichloroarsenic. Water was with nanoparticles, and after shaking, we finished with these nice films. So one is mirror film for very big particles, and for small particles, kind of like filtering film. How it works? Okay. So what I'm doing here is I'm taking the solution of TTF in dichloroarsenic, add nanoparticles, shake it a bit, and you see what will happen afterwards. The solution becomes less colored, right? I shake it a bit more, and the solution is almost transparent. So I can remove this solution, add more solution of gold nanoparticles. Okay, please. Bit of nanoparticles again. Again, you see that it's kind of like intense color, right? So I shake again, and magic happens. Solution is less colored, and there are some golden color and luster for nanoparticles in the liquid interface already assembled. A bit more effort, and it's almost transparent. and it behaves really like a drop of liquid gold. One of the important properties of this assembly that it doesn't form crack if you shake. Instead, it forms kind of like wrinkles if you try to tear it. So if you try to tear it apart, it forms kind of like structure that is binding together on nanoparticles. And now you can imagine this is like 10 nanometer nanoparticles linked together of the scale of what, 5 millimeter. So it's like 1,000, 100,000, millions of nanoparticles bind together. This is 20 centimeters 20 centimeters liquid mirror that we created for the NID seance in Geneva, I'll say some time ago in 2014. Okay, what is the origin of cell healing and what is the origin of this interaction? If we try to assemble just nanoparticles, so we have bricks, right? We try to do some wall out of the bricks, and we finish with these crumbles. So what you saw when you add salt to a gold nanoparticle solution, you have black crumble at the bottom of the pot. But if you add TTF molecules with a special PP interaction between them, so they can form stack one by one and so on, then those TTF molecules, they work in like Lego bricks, and with these Lego bricks you can build already a wall. Actually, I need to change for China. I think I need to change this picture for the Great Wall. Okay, fair enough. What we showed that we can control the amount that we absorb, so we can go very, very high, so we can form even multi-layer film. We showed that we can do complete removal of nanoparticles, meaning that we can, for example, from electronic waste we can create nanoparticle solution, and then with this process we can assemble them, so take out of the solution every gold atom. And this process is kind of like universal. We tested with like dozens of solvents, and for some solvents it works better, for some worse, but still it's working for many solvents. And what I said, that is particle connectivity and mechanical properties, I think it's very, very important, and this is where I'm trying really to find a partner in crime to investigate it and to quantify it, because this is really nice system where you can test and prove many ideas. Okay, so by now we consider only high interfacial tension. High, it means 25-30 millinewtons per meter. So without TTF we do not have any assembly. With TTF we have an assembly. Very clear. There are many solvents. Some solvents they have with water very low surface tension, extremely low sometimes. And I mean, as a researcher, sometimes you ask like, okay, what happens if I choose very low surface tension? Okay, we did that. Okay, we considered this previously. Yes, I did it. So we selected some nitromethane, propylene carbonate that kind of like alike as water. And what we observed that even without TTF we can assemble quite reflective film on the surface of these solvents. It means that in principle we can easily industrialize this process and make square meters of such film. But more important, that if we took this TTF and, for example, propylene carbonate, mix them, nanoparticles are transferred from water to propylene carbonate phase. And this is a bit unusual because normally nanoparticles doesn't like to be in organic phase because of different reasons of screening charge, energy balance, and so on and so on. But here we managed to transfer them. And again, this is because of very, very unique nature of TTF. And again, here the most important point here that in principle we can concentrate this nanoparticle. So we start with a reddish solution, we transfer those nanoparticles to propylene carbonate, and then we finish with intense dark color of the droplet here. It's simply because the absorbance is so high, and the peak is so broad that it absorbs all the light. Again, some pictures to show. For example, we did ETX mapping in STM mode, so in scanning transmission electron microscopy mode, where we clearly show that nanoparticles are separated from each other by roughly 5 here it's nanometer, 5 nanometer thickness of the film of TTF. And also what we showed and why this suspension is so stable and why we can concentrate up to 10-15% this gold ink, because we sharpen the distribution of nanoparticles by charge. So this is like zeta potential. In water it was like this, very broad. Some particles were at zero, so meaning that they're kind of like ready to aggregate. And in propylene carbonate, it's really like a sharp peak, and it's positioned roughly 35-40 millivolts, meaning that it's a really stable colloidal suspension. And again, unique nature of TTF, TTF-CP interactions allows us 3 things. It's a transfer of gold nanoparticles to organic phase, then improve charge distribution, and this improves stability of this colloid, and then protect particles from aggregation. This a small slide illustrating how it works in the reality. So if we consider from kind of like first principles, like not big maths behind these graphs, but if you consider like different interactions like capillary forces, like salvation forces that are of course higher in organic phase and in water phase, some line tension that depends on the curvature of the interface around nanoparticles and so on, it's very clear that without TTF we have quite big barrier that protected nanoparticles from reaching interface. So literally meaning that nanoparticles doesn't know that here there is a potential well where they can go. If we add nanoparticles, then this potential barrier can be overcome by shaking, for example. So it's enough energy to overcome this barrier. And the same happening here, except that when we add TTF, there is no more well. So it's a small well, and then nanoparticles in principle can go to organic phase. Okay, so that is always a physical chemistry part. Now I'm coming back to analytical / electrochemistry part. Why we study liquid-liquid interfaces? Simply because this area came from 60s when people started to think, okay, we have some peptides, we have some interesting molecules sitting on the cell membrane, how we can investigate their properties, especially redox properties, because it's important when you try to trigger some mechanism in the cell or understand why this cell is working like that and not in this way. And liquid-liquid interface, so interface between oil and water, it's an ideal model for a half of the cell membrane. So in principle, for many years, electrochemists, especially in Czech Republic, what they were doing, they were peeling off membrane, bringing it to liquid-liquid interface, and study electrochemical properties. We do it a bit in more modern way for some some other electrochemical purposes, like for hydrogen generation, like studying electron transfer, how it occurs and so on. This is just for you not to be scared. What does it mean, all this BA and TB, which kind of like solvents we used, and so on. In principle, in electrochemistry at liquid-liquid interface, we deal with the same as at normal electrochemistry, except that our interface is a working electrode itself. Okay, so we can polarize this electrode. So there are different type of systems: polarizable, not polarizable. All the equations are quite similar to Nernst equation in normal electrochemistry, and how it looks like, how CV looks like. So on one side we transfer support on electrolyte, for example chloride. On another side we transfer another support on electrolyte, for example cation of lithium. And in the middle, if we add, for example, TMA, so it's a tetramethylammonium ion, it will be transferring across the interface, and we see both ionic current and electronic current. This sometimes really makes sense because you cannot distinguish between ionic current and electronic current if you have charged species. Okay. Then the next problem that I faced was how to transfer nanofilm into 4-electrode cell to study property of this film electrochemically. And the problem was that many of previous studies, they were, I can't say inaccurate, but they didn't take into account many small details, and people who studied that finished it with very high Faraday currents and so on and so on. And it's simply because you cannot control amount of nanoparticles that you deposit from the solution to the interface. So it means that your experiment is not reproducible. Also, you add some alcohol, as I said, like ethanol, methanol, propanol, and so on. You have a muddy oil compartment. Okay, again, not good, for example, if we're talking about some Raman and UVVs and some optical detection. Again, main problems was contamination by gold nanoparticles that gives rise to Faraday current, effects of alcohol, and actually we have no idea about what the film we are talking about. We created kind of like method to deposit film at liquid-liquid interface. Again, coming back to the introduction, we induce locally, not globally, but really locally, this zero surface tension condition when we have gold nanoparticles solution concentrated in alcohol, and we deliver it directly to the interface. So you can see films. It can be like 2 square centimeters, it can be 8 square centimeters, doesn't matter. We reduce the amount of chemicals. We know exactly the amount of nanoparticles, so we know exactly the coverage. We do not have electrochemical pollution of the cell. That means that we can really study some and carefully study some electron transfer across the film. And of course, as we started to work with TTF, the first candidate was TTF. We did it without TTF. Then we added the film, added TTF, and surprisingly we saw some peak. It means that something is crossing the interface. Again, it might be electron, it might be ion, who knows. But then we shifted to ferrocene, that kind of like the same electrochemical potential as a TTF in organic phase. And for ferrocene we saw more or less the same. So we know that ferrocene is not interacting somehow not sticking to the surface of gold nanoparticles. We know that fluorescence is kind of like just giving electrons or taking electrons. And in principle, if you leave the system for a long time like this, fluorescence diffuses to the bulk of the organic phase or water phase, because it's charged, it can cross the interface. And this peak disappears with like after half a day or maybe a day. So these ion transfer peaks of TTF plus and fluorescent plus, because this is peaks of ions transfer, it's a sign of that those donors gave the electron to nanoparticles. And this means that nanoparticles kind of like positively charged, or their potential is lower than all this stuff. And based on that, we developed kind of like a theory explaining all these observed phenomena. So, for example, our gold nanoparticles level, Fermi level, or redox level somewhere here. With fluorescence we charge it up to here. With TTF we charged up to here. We can charge up to here. We can charge nanoparticles, but if there is no application, it's it's nothing. But before going to real application, we need to consider one thing. So we call it redox electrocatalysis, and I don't want to speak really much about that because it's too boring. Just to show you that is these experimental curves. There is no film. There is a film. You can see that here there are some problems with the CV. For people who are doing electrochemistry for a while, this CV looks ugly, but this CV looks just fantastic. It's just like from textbook. And if we are talking about simulations, we can simulate these CVs properly, but those CVs we can simulate just amazingly well. So gold nanoparticles also improve kind of like kinetics of all the reactions happening at liquid-liquid interface. And coming back to the application, we changed fluorescein to much stronger donor, like a decamethyl fluorescein. And this decamethyl fluorescein is known to reduce oxygen to peroxide or to water. The problem is that it happens in kind of like half an hour or half a day or 1 day scale, timeline scale. But what we did simply with and without film CVs in aerobic conditions, in anaerobic conditions, and we came to the conclusion that this is ongoing electrocatalytic wave, because there is no reverse wave. And again, the idea behind, we're charging our nanoparticles from somewhere from here up to here. We need some kind of like over potential or kind of like driven force, a bit more like this, and then from here electrons can go to aqueous phase and reduce oxygen to peroxide. And the presence of the peroxide was shown in shaken flask experiment with very known iodine method, and the yield of peroxide was about 20%. Not much, but we showed that nanoparticles really can work as a catalytic particles in unusual conditions for them, because natural pH and catalysis of oxygen evolution at this pH, on gold especially, it's almost not possible. But we showed that if we can molecularly charge and discharge, then it's possible. Okay, so about some perspectives, what is done. Large liquid mirrors, I already mentioned that. This is 5 centimeters, this is 20 centimeter. Also we played, and we recently published article on colloidosomes, some systems. You can form colloidism, so it's particles, so it's drops of one liquid surrounded by particles in another liquid. We showed that we can do some Marconi shutters, again, switching on and off. And what is not done yet is like, well, it's not finished yet. It's like self-terminated welding. I will come back to this a bit later. And cells and electrochemical cells on gold sponge electrodes. And also this is like one step closer to, because again, we can form nanoparticles thin reproducibly at liquid-liquid interface, so we know the amount of nanoparticles, their morphology, and so on and so on. So we can really go to interfacial electrochemical cells where we can select, by applying the potential, the molecules that we want to study. For example, we select, okay, there is no CE, but we select one potential, one molecule approaches the interface. We study Raman response from this molecule, we apply another potential, another molecule, we apply another potential, another molecule. And for example, if we can do every 100 millivolt per molecule window, such detection, so we can detect up to 7-8 molecules in our system. And in principle, the first attempt has been done by Robert Booth. In principle, it's very nice study. Another method that we recently developed is electrochemical drop shape analysis. Again, here we can play with different things. One key thing that I think it's really important, really useful, it's understanding of the electric field role in absorption and adhesion different molecules, especially drugs. Because again, liquid-liquid interface, it's a model system of our cell membrane, and all drugs, they should go across. And I think here it's like there are plenty, there is a field, the entire field, how you can use this technique to test some drugs. Not all of them, but some. I will talk a bit more in 2 minutes about this combination, porous electrodes and self-terminated welding. I met this guy, Edmund Magner, last year in Bologna at the International Society of Electrochemistry annual meeting, and he presented very nice work on gold porous electrodes. Unfortunately, I mean, the good result for him. So, okay, there are several examples like how you can use these gold porous electrodes and gold porous stuff. For example, the very amazing example, I think, it's like self-powered battery, let's say, or some kind of like source that is working on oxidation of glucose that you have everywhere in your in your blood vessels, in tears, in sweat, everywhere you have glucose or some kind of like metabolite of glucose, and they managed to make it a power source that you can implement inside of the lab. So you do not need any battery inside of the lab. The battery will eat and will find itself what to burn and how to generate electricity. Okay, the good results, to make this story short, the good results, very improved kinetics of the reactions, high sensitivity analytical applications. For example, I can detect oxygen level, I can use it for glucose sensor. However, there are several complications, so they do it through magnetron sputtering, and then they are alloying with very concentrated chemicals like acids, basics, and so on, and heating. And this is not good. You want to avoid this if you want to do some industrial process. And what we study, but unfortunately haven't finished that. As I said, we can prepare gold ink, gold nanoparticles surrounded by TTF in purple and carbonate, and then if we combine these, if we print these on some substrates like metal, glass, polymers, and so on, heat, it's like low temperature sintering process. Then we can finish with quite similar microstructure between what Edmund has in his articles and this self-terminated building procedure. And once again, so this is a bit more like how this gold nanoparticle sponge looks like. In principle, it works. So of course, some optimization and improvement are required. But however, if you clean electrode, it's already you already increase the current. If you sinter electrode, you really improve the kinetics of the reaction. And yeah, as I said, this is a preliminary study that we've done recently, but I think it's a good example how you can use this gold ink really to print with commercially available inkjet printer, just electrode whatever shape you want and whatever space dimension you want. Okay, so finally, I want to really thank my former supervisor, Professor Hubert. He's still running LEPA already for more than 1/4 of a century, for 25 years. Michael Scanlon, now he's in the University of Limerick. I visited his lab last year. It's amazing. Pekka Pegio, with whom we published a lot of electrochemical papers, and Dmitry Mamotenko, who left Switzerland to stay abroad for several years, and now he came back to not to EPFL, but to University of Zurich. And I think by now that's all. There is a list of the reviews that we wrote with all these guys. And how you reach me out, so please, your questions.